our estimated guest and fellow students, I Harshada Jagtap would like to welcome everyone to this session on Thermodynamics, a science to understood and solve problems, organized by IIM student chapter of COEP Technological University. We have an excited session ahead where we will get the opportunity to learn from an expert in the field. Dr. Avinash Kulkarni sir is a founder, director of 4 companies: Litex Electricals Private Limited, Little Infrared Systems Private Limited, Arclight Specialty Lamps Limited, and Aeropure UV Systems Private Limited. These companies launched several technologies for the first time in India, including halogen lamps for film and TV shooting, tungsten halogen infrared lamps, pulsed xenon lamps, metal halide lamps, germicidal ultraviolet lamps, medium pressure mercury lamps, extremely rapid heating systems for aerospace applications, UV germicidal irradiation system for the air disinfection, etc. He received BTech honors from IIT Bombay, PhD from University of Pennsylvania, Philadelphia, and MBA. He worked for 8 years as a senior research engineer in the lamp division of Westinghouse Electric Corporation in Bloomfield, NJ, USA, where he received a citation as inventor for getting 5 US patents. He is the recipient of the first prize of National Award as an outstanding SSI entrepreneur from the President of India in 1985. He is also recipient of Distinguished Alumnus Award of IIT Bombay in 1983. He was 2-term president 2002 to 2004 of ILCOMA, Electric Lamps and Component Manufacturing Association, an apex body to the lighting industry of India. He was also president of the Indian Society of Lighting Engineers for a term 2007 to 2011. Now I would request HOD of Metallurgy Department, Dr. Manisha Kulthe ma'am, to felicitate our guest speaker, Dr. Avinash Kulkarni sir. Thank you very much, ma'am. So without further delay, I would like to invite Dr. Avinash Kulkarni sir. On the dais, Deshpande sir, Manisha Kulkarni ma'am, and Manisha Kulkarni ma'am and Avinash Kulkarni sir. I would like to invite Deshpande sir to say 2 words.
Very good. I don't know what you call now, good afternoon or good evening, in between, 3:34. So, I think everybody is now, after lunch, little break, they are now eager to listen something new. I have to thank everybody here. Firstly, Professor Booty. I recall 2nd March last year, we met at Hotel Sheraton Grand, that is Blue Meridian. There was IIT Bombay director's visit, and I was standing in front of a lift of the 1st floor. I welcomed him, and we became best friends. Almost last 30 years, myself and Booty sir know each other because I was teaching in mechanical department for a master's since 99. But that was only face recognition. The director's meeting, or basically visit, changed our relations. Then last 1 year we are thinking what to do, where to come and all that. One of the such evening programs we organized at Institute of Engineers two IIT Bombay alumni. He is a 1963 batch, almost first or second batch. His batch has learned first in the IIT campus. Earlier, 1963 batch, we didn't have a campus. It was under construction, and it was at the Prabhadevi, Sasmira, that college was conducting classes. So he may be 83, 84 age, well, let us confirm, age is different. It is not a criteria, brain works. Super active, superconductor like that, he is super active. Goes with a fantastic idea, whatever our MOC has read, everything is perfect. And he is charging us by thoughts, by activities. So he may be 83, 84, and on 20th August we had one program at Institute of Engineers to 2024 BTech guys, BTech MTech dual program from IIT Bombay, very young last year. On 20th August we had a program of theirs in Institute of Engineers. Very few people, you can count on my fingers, have come. But that changed everything, and he has given me the idea. So he said, why not have such program? He heard somewhere Professor Bhuti's name, and that time it started on 20th August last year. Now we are here. Then each and every program, whenever I come to CIP, we met. He is too busy. CIP, all professors are busy than Prime Minister Modi. I am telling you, paperwork है, meeting है, ये है, and now you are exploring an explosion है ना, all पूरा work में, no time. But he was meeting me. When I call, he was meeting me. Then slowly it has come. So today is the 16th. Thank you, Professor Bhuti. Thank you, sir. So, now sir.
Okay, sir.
Dr. Doke, sir, who is the Dean, R&D. We had a nice meeting last week, and he has given us a vision what CIP wants, what we should do, and what we should not do. We didn't state what we should not do, but we understood. But he has given a guideline. So this is the way we are proceeding. I thank everybody here, and almost I am very happy. There are 6 or 7 IITians faculty here, and I have seen one faculty from IIT also, IIT Bombay. What is your name? Abhay Deshpande. He is also Deshpande like me. So I am happy. So gathering with new ideas, taking differently. Exactly I will ask, what is difference between CIP and IIT or any other college? IIT syllabus hai, there is some syllabus. It is taught 175 to 250%. Question paper, my professor Suhas Kapne was giving open book exam. If I open book, then only I will try something. Exact answer, no marks. Procedure and understanding is mark. So IIT, they teach out of the box. That is a specialty, I believe. So I talked a lot. I believe I should stop now. Okay, sir, I will request you to say something.
But I will not make much of no, it's okay. I think I'm audible to all of you. So let me welcome Dr. Avinas Kulkarni. And in fact, we know each other since last 20 years.
Yes.
And the motto of IIM Pune chapter, we have been organizing several events and guest talk and so many conferences. But the idea came when we met very enthusiastic Suhas Deshpande sir to have some kind of a get together. So we thought why not we will have a technical get together in CIP. We will learn something and then we can have some more networking. So we thought of having this idea, and there are several of the faculties from the IITs and some of our common friends from the IIT. So let's have this get together here, and that is why this the first initiative with the logo of IIT Bombay Alumni Association we started. thanks to Dr. Bhutti for this initiative. And the IIM Pune chapter, started here in this campus in 1948, and in fact established in 1947 in Kolkata. And the founder of this department, who founded this particular department in 1948, who is that time a common person to a chapter and this department, and therefore we are carrying this legacy since last more than 75 years. And in fact, last year we celebrated the platinum jubilee for both the the organizations, IIM Pune chapter as well as for this department. So with this, I will not take much of your time, and once again welcome you for this prestigious gathering. Thank you.
Good afternoon, ladies and gentlemen, dear students. I'm coming to this campus after about 2-3 years. I'm very happy to be here, and it all started with Professor Bhutti making an announcement. Can somebody give a talk on thermodynamics? For a month I was just thinking whether I should or not. Then I said, let me give a commitment. And last 6 months I've been working on this, because last 45 years I'm not in a university, I'm not an academic, I'm running industries. So this was for me a big change to come from, instead of looking at excise and sales tax, looking into delta G and delta F. Let me begin with the first slide. The outline of a presentation is actually these are all case studies. First we look into pyrometallurgy, begin with blast furnace. Shall I start? So we will begin with blast furnace. When we were undergraduate student, all of us had to go to steel plant for 2 months training. I don't know how many of people here have. Please raise your hand if somebody has seen blast furnace. You have seen blast furnace? Yeah, my God. Okay, I'm very pleased to that at least there are a couple of them. We spent 2 summers to April and May in Bhilai to taking practical training. Anyway, blast furnace, steel industry was the main employer of the metallurgist. And we'll begin with blast furnace. Then we'll go into systems near equilibrium. See, at equilibrium everything is fine, but you want reaction to go forward. So what do you do? Then we'll look at the equilibrium system. Then we'll look into some examples of hydrometallurgy, molybdenum recovery from waste acid, and optimization of ion dissolving in HCl. We'll finally end up with electrochemistry and go to the hydrogen economy in terms of electrolysis of water, IC engine, and then fuel cells. So to begin with, let's look at before we go into thermodynamics, let's just look at the basic formulas which we are going to use here. Delta G is equal to delta H minus T delta S is the basic equation. But in the literature, you will only find the values of delta H and delta G. You will not see the value of delta S. So you calculate delta S using the same equation at 298 degrees centigrade, because all the data given in the literature is for 298 degrees standard state. So once you have delta S calculated this way, then you can use this formula, delta G equal to delta H minus T delta S. So you can calculate the free energy of any compound or any reaction using this formula. You can do, this is a 298 now, you can calculate it, you can do T as 1000 and you can get delta G at 1000 degrees Kelvin. Okay. So this we will be using in the calculation. Another important formula which we will be using is for electrochemical reaction is delta G is equal to minus NFE. N is the number of electrons transferred in the reaction, F is the Faraday's constant, and E is the voltage generated by the electrochemical reactions. We will look into both of these in different systems. First, looking at blast furnace, as we all know, the feed is iron ore, hematite, coke, limestone, and air at a very high pressure. It's also hot air, preheated. The output is pig iron, slag, blast furnace gas, which is CO plus CO2. 55% is nitrogen because you are blowing air inside anyway. So it turns out the CO and CO2 are about the same, and this frustrated the earlier metallurgist. Any CO leaving the blast furnace is a waste of energy, they thought. It should be CO2 which should be leaving. So they kept increasing the height of blast furnace and made bigger and bigger blast furnace. So this was since the invention of, it was invented in 1709. They were not understand. They could not understand. They made the biggest blast furnace, tallest blast furnace, but they had the same results. So they knew that if you can have lower CO, you will have more efficient blast furnace. But made it taller and taller, but did not help. So let's look at why this is so, and let's look at the mystery of low CO in the output of blast furnace gas. As you know, this we have iron ore, coke, and etc. being fed from the top, and this is about anywhere from 100 to 200 feet tall. In the state of the art blast furnaces give 5 to 8 million tons of pig iron per year. So this must be about 100 feet tall or 125 feet tall blast furnace. As you can see, all this limestone, coke, and ore is descending down, and here is a temperature profile given there, right from here got in the bottom, the slag is being tapped because slag is much lighter than the pig iron, and the pig iron is being tapped from here. So there are so many reactions. Hematite reacting with carbon monoxide giving magnetite and CO2, then magnetite reacting with carbon monoxide giving FeO and CO2, and then FeO finally reacting with CO and giving us CO2 and iron. But do you realize that this reaction is the most important, because 1/3 of oxygen is eliminated by these two equations, and this eliminates more oxygen than these two put together. FeO, the iron to oxygen ratio is 1:1, and in Fe2O3 it is 1:1.5. So this is the most important reaction. So we will look at the thermodynamics of this reaction, and that this actually, to say that because there are too many reactions going on simultaneously, like here, the limestone is also decomposing, coke is reacting with CO2 forming CO, limestone is also decomposing. There are too many reactions going on. We will just look at thermodynamics of just one most important reaction, which is FeO plus CO is equal to Fe plus CO2. FeO, I just rounded off just for the illustration. The delta H and delta G is all this CO2 is like this. So when we calculate, first thing we do, as I said earlier, is to calculate delta S. Delta H minus delta G divided by 298. So now you can calculate the free energy change of this reaction Fe plus CO CO2 using this equation. Now this R is about 2, and this when you go from natural logarithm to base 10, there's 2.3. So these two just together become 4.75. So let's now go to the next slide. Now this represents the equilibrium between FeO and CO CO2 and iron, of course. Now okay, yeah. So if you take temperature like 1000 degree Kelvin, then the CO is 62%. Actually, CO CO2 ratio is important. Their absolute value is not of importance, because the oxidation potential depends on the ratio of the two. If the temperature is 1600 degree Kelvin, then you have CO is even higher. Now these are the equilibrium conditions. If you want the reduction to occur, actually CO has to be higher. Fortunately, there are other reactions taking place in the upper part which give more CO2, but it is very clear that amount of CO is going to be predominantly going to be a very important component of the blast furnace gases, and you cannot reduce it because it's a thermodynamic limitation of the reduction of FeO. So Actually, as I said, even now they are satisfied that if CO2 is about equal, you are doing okay. So this is how I would say the first mystery of the steel industry, blast furnace, was resolved by thermodynamics. I don't know, maybe in the last century. I don't know when they did it. Let's go to the next slide. We saw this system and we calculated the CO meant for equilibrium. But you know that for the reaction to go forward, the CO has to be even higher to get the reaction, to give a decent kinetics for the reaction. Now we'll go into halogen lamp. This is the field I have been working for the last 40, 50 years. This is a small halogen lamp here, 500 watt. Here along the axis is a tungsten coil, and here there is a pitch seal, and there are support rings of tungsten, and this is filled with about 2 atmosphere of argon and a trace of halogen. I'll try to explain what happens. If the filament is 3000 degree Kelvin or 3000 degree centigrade, tungsten is going to vaporize. And where is it going to go? It is going to stick on the wall. So, tungsten vaporizing and sitting on the wall, and wall temperature may be 700, 800 degree Kelvin. Now when you put bromine or iodine at 700 degree Kelvin, this oxygen, there is always trace amount of oxygen in the lamp. They react with tungsten sitting on the wall of the lamp, and they form this all kind of fancy bromides and oxybromides. Now these bromides and oxybromides, by random motion, they come and touch the filament. When they touch the filament, they decompose, and the other reverse reaction takes place. Say one oxybromide going back to tungsten, oxygen and bromine. So tungsten deposits back on the filament, so you keep the wall clean. So bromine or iodine is going around cleaning up the wall. So this system, the life of the lamp is 2000 hours. So this is a near equilibrium system. Now we look into the traditional way of doing this and what we thought was a better thermodynamic approach. The traditional way of making bromine is to have cylinders filled with argon and with methylene bromide. Methylene bromide is a gaseous product, gaseous compound of bromine, and it is mixed in the cylinder. And all you do is the last step, you evacuate, clean up the lamp, and put argon and methylene bromide and freeze everything. And but if you want to control bromine, you want to control 0.1, 0.2, or even up to 1.5%. You need different cylinders with different amount of methylene bromide. In Westinghouse, we used to have a dozen cylinders with different amount of methylene bromide. Well, this was a standard process. I thought of doing something else. I said, why do you need a cylinder? Why can't we use some bromine compound? So we tried. Mercury bromide could decompose into mercury and bromine. So what we did, take some mercury bromide, dissolve it in methanol, and take a very few 10 microliters, dispense it in the lamp. Now it's a methanol, so it vaporizes. So you are putting a very measured quantity of micrograms of bromine into the lamp. Now what happened? The company was not able to manufacture the stage and studio lighting lamps because they are the most demanding, because temperature of the filament there is 3200 degree Kelvin to 3400 degree Kelvin, which is almost 0.9 times the melting point of tungsten. So these are they were able to, either the lamp will blacken or they will fail early. But when they use mercury bromide, you will see here, if the life of the lamp, rated life is supposed to be 50 hours, because this color temperature of this lamp is very high. So we could use for bromine, you could use from 4 torr to 8 torr and still gets a good life. So with this technology, Westinghouse was able to launch this whole series of stage and studio lighting lamp, and this resulted in a patent called, as you can see, US patent Westinghouse, and they were able to enter this particular new range of product using this technology. I would like to show okay, how this lamp is sealed. This quartz glass, the oxyhydro flame is rotating burner about 10-15 seconds. This is the second side. First side is sealed. Now you are continuously passing nitrogen through so that you cover the tungsten filament so that otherwise it will get oxidized. Second side is also sealed. So this is now this lamp is now ready for putting inert gas and bromine for making the finishing, what we call exhausting the lamp. Now we saw one bromine technology, how the traditional technology was changed from this by using mercury bromide. Now the halogen lamp was introduced sometime in 1958. In that time the halogen lamp meant iodine lamp, because iodine was the most, as you know, 7th group, fluorine, chlorine, bromine, iodine, actinium. So this is most safest one to work was iodine, and iodine vapor pressure, you see, sorry. This is iodine vapor pressure at 60 degrees, 4.4 torr. This is about the amount of iodine you want in the lamp, 4 torr or so. Now you have seen how we make this lamp up to this point. Now this lamp is already filled with 2 atmosphere of argon, and you have to put iodine. So they put a pinch of iodine in the exhaust tube and just heat it so that it's only milligram. So it melts and stays there. Now if you want to dose iodine, you put the whole lamp at, say, if you put the lamp at 60 degree, the iodine pressure will be 4.4 torr. But you will have to put that for half an hour, 45 minutes, because it will take time for iodine to vaporize and fill and come to equilibrium, come to steady state in this step. But in manufacturing, who has got the time to wait for half an hour? So they use temperature like 100 degree or 120 degree, and they use only for 1 minute, 50 seconds, 50 seconds. So naturally, going to equilibrium is too time consuming. So for the sake of kinetics, they increase the temperature. And actually, as one of the trial experiment, I tried to fill lamp with different amount of iodine by using the temperature, holding temperature like 60, 100, 120, 130, 140, and I made all those lamps and measured their lumen output. Because as you increase the iodine pressure, the iodine is a very purple color gas, and so it absorbs. So more iodine you put, less is the light output, and so lumen per watt drop steadily as you increase the iodine. What was my solution to this? I thought this was a very long process. So instead of using iodine element, why not try some other compound like tin tetraiodide? Now I went through all kinds of halogen compounds and zeroed on this tin tetraiodide, because tin tetraiodide would be decomposed into SnI2 and I2, and if you dissolve this SnI4 in alcohol, inject maybe 10 microliter, 20 microliter, so you have dispensed a precise amount of iodine in the lamp. And now you exhaust the lamp. You don't have to do that sitting in the tub for keeping the lamp at 50 degrees centigrade for 2 hours. You already dispensed, and then you can exhaust the lamp, fill it with 2 atmosphere of argon, and the lamp is ready. So this was a ridiculously simple process compared to what it was earlier. Now they decided to take trials. So we had, on 4 consecutive days, we made lamps using both processes, using standard traditional iodine process and using SnI4. So here are the results. You'll be surprised. This is October 74, almost 50 years old. Yes, yeah. Okay. So you can see with SnI4, the top 4, you can see all consistent. Nothing is below 20.5, And with traditional iodine process, the process control is very poor, because some lamps are staying much longer in the hot water. Some lamps are being taken out much earlier. So you can see the variation of what you call light output of the lamp. As I said, the higher the higher the iodine, lower is the light output. So you can see here, first day, second day, look at the second day's variation. Third day something went wrong. So, and fourth day again. So the average of all these lamp for SNI4, we had 21 lumen per watt, while this was 18.8. So clear 10% improvement, and what is more important, the process control is very precise. Anyway, they never used this technology because they were so comfortable with buying their conventional process that I could not. You can only bring the idea and get it patented. Whether the engineering department accepts it and changes the process is up to them. So this of course resulted in another patent. You can see regenerative incandescent lamp with SNI4. So this was another patent which resulted from this. I just want to give an idea. I was telling you that we fill these lamps at 2 atmospheres, some we fill 3 atmospheres. How do you do it? When you fill a lamp with 3 atmospheres and try to seal it means you melt it there. When you melt it there, it is 3 atmospheres, it's going to blow out. So what do? We do what is called cryogenic filling. That means, that means this halogen lamp is on the exhaust bench. You isolate, you fill with 2 atmospheres in the manifold and isolate the lamp from the manifold, and slip a liquid nitrogen cylinder around it. So liquid nitrogen will freeze argon, and the vapor pressure of argon and liquid nitrogen temperature is only 200 torr, so which is 1/4 of the atmosphere. So the pressure inside the lamp is now less than atmosphere. You seal the lamp. When it comes to room temperature, it's 2 atmosphere. So this is called cryogenic filling. Can you believe we used to make 1 lakh lamps a month, and the price of this lamp is like 30 rupees. So we just stopped making this lamp because it didn't make any sense. Go through all this process and get 30 rupees. It's not worth it. So anyway, so this is how we make. I thought so cryogenic filling was a good technology, and again depends on the vapor pressure and temperature relationship of any gas. Now next we will talk about coil making. See, all these lamps have got tungsten filament. The lower one is coiled coil, you can see. Coil, and that coil itself is coiled. This is a single coil, and this is a segmented coil. There is a coil, there is a gap, again coil, gap. Now how do you do this? For making this, you first wind this tungsten on a mandrel. Now what kind of mandrel you use depends upon what is the temperature this lamp is going to operate. Now here, this is the most demanding of all these applications. So here you use molybdenum mandrel. Here you can, some of the lamps you can get away with it iron mandrel because the application is not so demanding. So you do the coiling of the lamp. Coil making is done this way. This is an automatic machine, numerically controlled. The coil is made. Now for making the filament, winding the filament, you, as I said, you either use iron mandrel or use molybdenum mandrel. Iron mandrel is for lamp which are not so demanding, so which you can heat up to 800-900 degrees centigrade. If you heat higher, the tungsten gets contaminated. But if the application demands that it should go to 1600 degrees centigrade, 1700 degrees centigrade anil, then you have to go to molybdenum mandrel. So to retain the shape, you have to either to go to 800 to 1800 degrees centigrade. So 800 degrees centigrade is iron mandrel, and once the mandrel is formed, you cannot pull it out. So you have to dissolve it. So normally, normal process for dissolving iron metal is to dissolve in HCl. Okay. But for molybdenum, you use a mixture of sulfuric acid and nitric acid. You dip it, then all the mineral dissolves and your coil is clear, and you just clean the coil and make the lamp. The next two processes are for recovering molybdenum from spent acid and to minimize HCl consumption in this whole dissolving operation. Let's look at these two processes. Recovery of molybdenum from spent acid. Now you got thousands of coiled coil in which molybdenum metal is there. You put it in nitric sulfuric acid at certain temperature, and after a while the molybdenum dissolves, and the acid has a limitation. It can't dissolve any amount of molybdenum. Say about 80 grams per liter, it stops dissolving. So what they did, they discard the acid. Now use fresh acid. So one of the, I think very first few months I was investing was, I thought this is a colossal waste. I should do something. This has nothing to do with my project. So I started working on this idea, and found out it's a molybdenum dissolved in aqueous solution. So molybdenum is going to exist some kind of MoO2 plus. In fact, there are many more species of molybdenum. So I realized there's something called isoelectric point. I did not know what exactly it meant. I found that it meant the net charge on a species is zero. That means you have your positive charge, your negative charge species, the net charge is zero. It was just logical that if net charge is zero, they should combine and neutralize and settle down. And since there was so much of other ions present, so what I did was and this isoelectric point was between pH of 2 and 3. What is going on? So isoelectric point is between pH of 2 and 3. So I took the acid, the normality of it is 15 normal, it's highly acidic. You put ammonia, bring the pH to 2 and 3 and hold it overnight, and surprise, all the molybdenum precipitates has ammonium tetramolybdate, 99% recovery. So in the meantime, there were some other projects where they were thinking of distilling this molybdenum acids and recycling it. But this turned out to be an extremely simple process, and so this technical paper called, we also got a patent, and we also got technical publication in metallurgical transaction. And this process became standard in the whole industry, because GE and Westinghouse will exchange patents and Sylvania will patent, so this becomes standard in the whole industry. So this is the first patent which I got in February 1975, that was 50 years ago almost, and molybdenum recovery from spent acid. This is the graph. As you can see that between the pH of 2 and 3 is almost complete, 199% recovery. So the process is spent acid, put ammonia, adjust the pH to 2 and 3 and stir it for 10 to 20 hours, add wash water and then filter, and this is okay. 10 years later, one of my colleagues filed another patent on this. He said, why do you want to wait for 10 hours? He just put some ammonium molybdate to begin with. He did seeding. So instead of overnight, it became 3-4 hour process. See, this is what it is. I never thought about it. So somebody later on thought that, why should I wait for 20 hours? I can just put seeding. And so this process has even improved still further. Now let's look at the other process of dissolving HCl, using HCl for dissolving iron mineral. It's 30% acid is standard. Even in India, if you order HCl, it's 30%. America, also 30%. So all they did was took out the acid, put it in a reactor, heat it, put those tungsten coil, put them in that and heat it to some 60 degrees centigrade. It used to give a lot of HCl fumes, and anyway in some time it will dissolve. Again, when I looked into this, I thought, now this process, can you believe, it was at least 30-40-year-old process. But if you look at phase diagram, HCl in water system, you realize there is a azeotrope at 20.2. That means it's a constant boiling. It's at 108 degrees centigrade, the HCl and water boil at the same temperature. It's like alcohol. Alcohol with 4% water is azeotrope. You can't separate, you can't increase the alcohol percentage by distillation. Same is here. The azeotrope. So I said, why not try this? If you can, azeotrope boiling point is 108. So the process modified was, so here is a technical reason. Another reason, if you reduce the concentration of HCl, the solubility of FeCl2 increases. So you have double advantage. You are using 20%, you are diluting the acid. At the same time, your solubility of iron is increasing, and now you can jack up the temperature to 80 degrees centigrade because vapor pressure of HCl is so much lower. It is 20-25 times lower. At 20.8% and 30%, it is 20 times lower at 20%. So you can raise the temperature, and here is the azeotrope, that vapor pressure of HCl and they boil same time at 108 degrees centigrade. The solution was, take a 30% HCl, make it 20.2, this go to azeotrope mixture, raise the temperature 80 degrees centigrade for faster dissolution, and lower concentration HCl, you can use higher temperature and you have bigger solubility of iron. HCl consumption goes down to 40%. What you are using was 100, now you can do it 40. This innovation was not considered patentable. It was used as a trade secret, and so it doesn't matter. I get $100 award anyway. So now this was not the end of it. We thought we can improve it, make it zero discharge. How do you do this? The spent HCl, you use peroxide. So ferrous gets converted into ferric. The beauty is when iron is present in ferric form, it is not FeCl++, it is FeCl4 minus. So trivalent iron in HCl is actually an anion. So what you do, you take the solution and pass it through an anion exchange resin. So it will capture all the FeCl4 and the HCl is regenerated, you can reuse it. And FeCl4, you can wash it down with water and get FeCl3. So here there is an opportunity to you make almost zero discharge. All the acid is being recycled. There is no waste. So, but anyway, they never went to this because they were quite happy with 40%. Both fayda ho gaya that, we are not greedy. They were quite happy with their whatever they had received. Now I am turning to electrochemistry. First, let's look at what is grey. We are talking about hydrogen economy, and there are two terms which are very frequently used. Is it grey hydrogen or is it green hydrogen? Grey hydrogen is the one which is derived out of decomposition of, say, methane. You decompose and get hydrogen. That's grey hydrogen. But if you do electrolysis of hydrogen, that's a green hydrogen, especially when you do it with a solar energy also. Okay. Now you look at thermodynamic parameter of H2O, gas and liquid. Here is delta H, is delta G, and so forth. So delta G of water is the liquid is 56.7. If you just put it NFE, N here is 2, F here is 23.6 kilocalorie per volt, and E is the voltage. So you calculate the voltage of this electrolysis is 1.23 volt. Which is standard. You take water, put some acid and do it electrolyze, you get hydrogen and oxygen. No, it's nothing surprising. But what is surprising, that if you again try to create hydrogen and oxygen together through electrochemical process using hydrogen oxygen ion conductor, that means create a fuel cell, then also you will get the same 1.3 volt. That means you are talking about the reverse reaction, O2 plus H2 forming H2O. This also will happen at same voltage. Of course, there are some inefficiencies. So this voltage may be 1.24, 23. That voltage may be 1.3 or 1.4 also. But this is a reversible reaction. You can. But for that you require an electrolyte, which is oxygen ion conductor. So normal conduction is electron conduction. So how do you create ionic conductor? Suppose you have zirconia. You dissolve zirconia valence is zirconium is 4. You dissolve magnesia in it. Magnesium valence is 2. So for every magnesium which is taking place of zirconium, you are going to create 2 vacancies of oxygen. So you are making that ionic conductor. So ionic conduction is what you require for making a fuel cell. And unless you have, so far, there is no practical hydrogen fuel cell, at least in the common use, because of the electrolyte. If we can get the electrolyte with very high good oxygen ion conduction, we can solve this problem. I want to end this slide with a very important, from metallurgy point of view, metallurgy of aluminum. Aluminum in 200, 300 years ago was as expensive as gold and silver. It was Hall Herold who found out, who took aluminum oxide and dissolved it in what they call fused cryolite, AlCl33NaF. You dissolve it as a fused salt and you dissolve alumina and you electrolyze it. So bottom is cathode, where all aluminum is reduced and collects at the bottom, and the oxygen goes up, and this is how we manufacture aluminum. This is a standard process globally. So what I am saying, this whole electrochemistry, one of the biggest example for a metallurgical application is the metallurgy of aluminum using electrochemistry and using this fused cryolite as an electrolyte. Again, it has to be an ionic conductor. If it is an electronic conductor, it will just short circuit it. Now let's look at this very fascinating thing. You can use hydrogen in an IC engine as a fuel, just like diesel or petrol. You can use oxygen also, hydrogen as a fuel. But you know, once you use hydrogen as a fuel, as an IC engine, you are limited with Carnot cycle. Carnot cycle, adiabatic compression, adiabatic expansion, isothermal compression, isothermal rate. So that limits is, you can't go beyond 35%. But if you use fuel cell, now look at this delta H is 57.8, this delta G is 56. It's about just a kilocalorie apart, it's about the same. But when you use this formula, the entire free energy is getting converted into energy, electrical energy. So what I am saying, that here you are getting 35%. If you use fuel cell, convert hydrogen using what you call ionic conduction of oxygen, you can get efficiency like 80-90%. You can double the efficiency of an IC engine if you use hydrogen fuel cell. Hydrogen as a fuel and hydrogen as a fuel cell makes a huge difference. So you can see how important this whole development is. Now here I am going to talk about something I know very little, but I cannot resist talking about it. How does human body work? Human body, we have glucose, C2H, and the end is glucose is aldehyde group, is a glucose. And if you have fructose, it will be CHO here, CO here, ketone. Now glucose plus 6O2 plus is equal to CO2 plus H2O. If you use the same formula, delta G is equal to minus NFE, you get a result again very close to 1.24 volt. But this result is not really it's accurate at all. Why? Because for this formula to be applicable, you have to have glucose in standard state, which would be in pure solid state, It means oxygen is at 1 atmosphere. Actually, it may be in 0.2 atmosphere, or it will dissolve something in the body, human body. CO2 should be at 1 atmosphere, which is, in our case it will be only 1/10 of an atmosphere, and H2O is there. So anyway, this tells that our whole body is actually electrochemical oxidation of glucose. And I tried to understand it. This 1.24 is a theoretical value, and standard set is, there is nothing in standard set in human body. This oxidation of glucose is very complex and happens in numerous stages. Let's look at very quickly. This some of the compounds. The most important compound is ATP, adenosine triphosphate. This all body is able to generate these chemicals without any effort, it seems. The oxidation of glucose is a very complex process. Food is consumed as a source of carbohydrate and it is converted into glucose. ATP is very important, and ATP reacts with glucose. It doesn't react directly with glucose, but degradation products of the glucose, and form complicated compound like NADH, FADH2, many others also. And oxidation of NADH leads, a formula of NADH is this, a formula of FADH2 is this. It regenerates ATP and produces electricity and produces CO2 or H2O. Amazing. When we saw glucose oxidation, we saw CO2 and H2O together. But none of these reactions have, either they produce CO2 or they produce H2O. In any case, there are maybe half a dozen steps involved. Each of them follow thermodynamic law. But just now look at what does it mean? The regenerated ATP reacts against the glucose and the cycle continues. It's like halogen cycle. The bromine, iodine again decomposes, hitting the filament, and again recycles completely. Here ATP is also doing the same thing. Oxidation is an electrochemical phenomenon. It is based on ferric to ferrous. Like RBC is in ferric, they will become ferrous. And this is the oxidation process, how it processes. It's very complicated. This electricity leads to muscle contraction, which produces mechanical energy. Muscle contraction is responsible for all internal and external body functions. This is something was not so obvious to us. Now just look at I thought it would be very interesting information to look at what human body is like. This last 5 minutes. Body has about 640 muscles. And the energy has to be generated in situ. You can't transmit, it's not like a fuel cell or cell in the body, you transmit electricity from there. It has to be generated in situ, in the muscle itself. So, in situ electrochemical oxidation of each muscle has numerous cells. The total, this is just an interesting fact, total length of arteries, veins and capillaries is staggering 95,000 kilometers, not meters. Out of which arteries are 160, veins are 200, and capillaries are in billions. We generate about 8,000 kilojoules of energy every day by oxidation of glucose. 2/3 of this is consumed within the body itself, with pumping of the heart and brain. Brain is just 2% of the body weight, but consuming 20% of the energy. And all this happens at 37 degrees centigrade. It's just an amazing thing what our human body is. I'll just summarize what I said. We covered a wide range of applications, halogen lamp at 3000 degrees centigrade to blast furnace 1500, and human body at 37 degrees centigrade. Thermodynamics is everywhere. We also looked into applications of aqueous solution, in aqueous solution like hydrometallurgy, like molybdenum extraction and HCl dissolving, iron dissolving. Highlighted major differences normal equilibria and those involving electrochemistry, electrochemistry delta G minus NFE. Fuel cells, using fuel cell efficiency of output could be doubled. Application of thermodynamics is almost universal, as areas involving nuclear, subatomic, quantum phenomena being exceptions. This I don't think thermodynamics is applicable there. Energy production in human body is an extremely complex fuel system. Acknowledgements, my friend here, Ashish Thorat, the engineer in our company, he's helped me putting this PPP, the PowerPoint presentation. I am pretty illiterate in these things. My grandson, Rishabh Bapat, who is doing PhD in National Brain Research Center, Manesar, he is the one who explained me, Adoba, this is how human body works, this is how the glucose oxidation takes place. So I am related to him. And thank you. Any questions, if you have time? Don't ask me anything about human body and glucose. I will have to refer to my grandson. Thank you. Yes?
I wanted to know
Just. Yeah. Oh, I see. Okay, which I discovered it by chance. Thank you. I am surprised that a 30-40-year-old process, they had not looked into azeotrope. You know, it was such a common thing that just put 30% to you go 20%. The process just improved by a factor of 5. So, anything else, sir? Yes, sir.
Yeah, just I wanted. Now, you told us that you have all this patent. So how you converted them into the products that you are doing? So many of all 4-5 industries. So where you are used to in your product?
Actually, see, this concept of liquid dosing I have used. I don't use mercury bromide. I don't use 10 tetraiode. I use something else. But the concept of liquid dosing, this invention made it possible to do it in SME. Because if I have to have 10 cylinders of argon filled with different amount of methylene bromide, I can't afford it. I can't run the industry. Getting one cylinder is bad enough. Getting 10 cylinders with different amount of methylene bromide is impossible. So this invention made it possible to do halogen lamp manufacturing is SME. So when I discovered this, I can use it. And actually, I asked my patent attorney, Dan Buleza, he used to come every quarter, and we used to submit our patent disclosures. He said, do you patent this in India? Hey, we don't patent in India. We patented in Taiwan, Singapore, in Japan. We don't patent in India. Good, I said. So actually, liquid dosing concept I used, but I am not using this mercury bromide or tin tetraiodate. That's. We have several patents in India also. I did not. Anything else? Yes.
How these isoelectronic materials are used?
Isoelectric point. See, isoelectric, when you have ions in a solution, in a liquid, then there are a lot of ionic species. Like if you take sodium sulfate, there is only a sodium and a SO4 minus and sodium plus. But when you have complex like molybdate, they have lots of ions, different MO2 plus and MO3 and so many ions with plus minus signs. There are many various ions. So and their composition changes with pH. So isoelectric point is a range in which the charge there are equal charge in molybdenum in positive and negative. So they will come together and crystallize. In this case, is so much of ammonia we have got 15 normal acid which have neutralized the ammonia. So there is a huge amount of ammonium ions. So that's why you got ammonium tetramolybdate. You got 4MO, 3,2 and H3H2O. I did X-ray diffraction and a 92% MO3 MO. We confirmed. Anything else? Yes, sir.
Very generic question on the presentation you have given to us. Regarding this patent, what you have shown,
Yeah.
you must have done numerous experiments on coming to this particular invention
Yeah.
before writing the patent.
Yeah.
So my question is that normally we talk about thermodynamics because our presentation titles
Thermodynamics. Yeah.
But many times the reactions are thermodynamically possible, but they may not be possible kinetically. Right? So, I mean, this is possible.
See, what is difference? Thermodynamic reaction is when forward and backward reactions are same. Then it's equilibrium. Okay. So now you put more of reactants, the reaction will go forward. And when it's equilibrium is when both reactions are equal. Backward reaction, forward reaction is same. But to push, you need kinetics. Kinetics you can use, for example, in case of reduction of iron ore, you increase the CO, the reaction goes faster. I have certain experiments for thermodynamics for your students. I can suggest you. They will explain the principle. I'll give you an example. Take a quartz tube, put a piece of iron in it. Pass argon over it so that it doesn't oxidize. Now take hydrogen, bubble it through water, pass it over it. Now H2O is there, H2O is oxidizing. So you can have water at 10 degrees centigrade, you will find iron doesn't oxidize. You go to 20 degree, 30 degree, 40 degree, the vapor pressure of water is increasing. So H2O or H2O is decreasing, it is becoming more oxidizing. You can find at what point at that temperature H2O or H2O is in equilibrium with FeFeO. Such experiments could be done which will really illustrate the principles of thermodynamics. Instead of just mugging delta G is equal to minus NFE or delta S minus T delta S, if you do this experiment you will remember it forever.
The importance of partial pressure will be more illustrated.
Yes. H2O when you are bubbling through water at 10 degrees centigrade, you know the partial pressure of water at 10 degrees centigrade. Your hydrogen is at 1 atmosphere. So H2O ratio you know. And when you go to 25 30 degrees centigrade, H2O pressure is increasing at 3, 4, 4, 10 fold also. So you can increase the oxidation potential. Yes. Anything else? What? High energy?
He is worrying about your energy.
When you love what you do, there is no dearth of energy. Anything else?
I think only thing which is older than the reactions is his age. That he is actually was in college about 70 years back.
Yeah, that's right.
65 years back.
Yeah.
I still remember the thermodynamics.
Yeah, it's very confidently.
Yeah, I did my PhD. I finished in '68, and then I have gone to university to learn. And I never sat in a classroom or taught anybody. I still have.
Still you make it so simple that anyone can understand. That is good.
I hope it was clear enough.
It was very, very
Yeah. Okay. Thank you all.
Everyone, our students as such, at our age also, we were afraid of thermodynamics. Now also I find the same thing, I teach that subject. that experiment will definitely plan.
Thank you so much, sir. Your insight have helped us understand the subject from real world perspective, which makes a huge difference in our learning. As we proceed towards the conclusion, I would like to invite Professor Butti sir to present a token of appreciation to Dr. Avinash Kulkarni sir.
This is
Thank you very much, sir. Now, I would firstly thank our guest, Dr. Avinash Kulkarni sir, for today's lecture, our respected faculties for their unwavering support, and last but not the least, my fellow students and audience for making this event a huge success by their presence. Thank you so much, everyone. Refreshments are arriving shortly.